All right, so we left off, we were doing some arithmetic with complex numbers, right? We had talked about adding, subtracting, and multiplying. All of those were really simple, right? The only thing that's any different, well, essentially you're treating the I like a variable when you're adding and subtracting. When you're multiplying, the only difference is that wherever you end up with an I squared, remember, I squared is always equal to -1. So when you FOIL out two complex numbers, the I squared term, you just turn that I squared into a negative, which changes the sign of that number is all, right? Okay, now today first thing we're going to look at is dividing complex numbers. And this is slightly more complex, no pun intended. So when we divide complex numbers, we rely on something called a complex conjugate, which I'll explain in a second. But first, let me define that. You might remember going back to earlier in the year, we talked about, I'll go down here. We talked about conjugates. We haven't talked about them a lot, but you remember saying that these two binomials are what we call conjugates. When you have terms that are in the form a plus b and a minus b. We're going to talk more about this. One of the places where this came up was when we factored a difference of squares. A squared minus b squared equal the product of the conjugate factors. Right? So if I multiply conjugates, I always end up getting, a plus b times a minus b. I get a difference of squares result, a squared minus b squared. Give me a thumbs up. Does that make sense? Do you remember talking about that? Okay. Right. So I have to doing weird things.
Yeah, now I just heard it.
Okay. Does it seem better now? Okay.
Yeah.
Let me know if it happens again. I can go to my desktop mic, which doesn't sound as good, but it's more reliable. I'm on my wireless one right now. So what I was saying then, did everybody get the bit about the conjugates there? Everybody heard that part? Okay. So when we have conjugates that are complex numbers in standard form, remember our standard form for a complex number is, and let me look back on something real quick here. I want to look back through the other day. Yeah, okay, we did. So we've talked about complex numbers in standard form that have a real part and an imaginary part, right? They're in the form a plus bi, right? So if I multiply two complex numbers that are conjugates, we call those complex conjugates. So those would be complex numbers of the form a plus bi times a minus bi. Well, instead of getting a squared minus b squared times I squared is -1. So the result is always a squared plus b squared. If I multiply out complex conjugates, I get a squared plus b squared, right? Now we can show that once. Let's go ahead and FOIL this out one time just to see it in action, right? If I distribute the 8, I'm going to get 64, right? 8 times 8 is going to give me 64 plus 8i. If I distribute the I, I'm going to get, that should have been a minus, shouldn't it? Whoops. Yeah, let me fix that. And then when I distribute the I, I'm going to get a plus 8i minus I squared. So look, the cross terms cancel, right? The O and the I of the FOIL cancel, just like they would with the regular conjugate. But instead of getting a minus 1i squared is positive 1, right? So I just end up getting the result 64 minus -1 is plus 1 equals 65, right? What is B here? Would everybody agree that these are complex conjugates where A is equal to 8 and B is equal to 1? Everybody agree? Okay, in other words, that's 8 plus 1i times 8 minus 1i. We don't write the 1, but it's there. That's our value of B, right? B is always the coefficient of I, okay? B is the imaginary part. So I could have just immediately said, well, I know what's going to happen when I multiply out complex conjugates. I'm just getting a squared plus b squared, which is 65, right? So over here, what does this amount to then? These are complex conjugates, so what's my answer going to be? What's A, everybody? Show me fingers. What's A? A's 5. Okay, what's B? 4. Okay, good. So A is 5. B is 4. The product of complex conjugates is just A squared plus B squared, which is what? 25 plus 16 is 41. Done. Okay, no big deal. All right, there's a reason we did that, and you'll see why here in just a second. So when we divide complex numbers, here are the rules. Just like when we simplified square roots, we had a rule of no irrational denominators, no tenths in the basement, right? We had to rationalize denominators and get rid of all the radicals in the bottom, right? A similar thing is true for complex numbers. We can't end up with i's in the denominator, right? Because ultimately, when we're all done dividing these numbers out, we need the result to be a complex number in standard form. So our result always ends up having to look like a plus b times I, where a is a real number and b is the real coefficient of I, right? Okay, so we've got to be able to get that I out of the denominator. So what do you think we're going to do? Like, let's look at number 13 real quick. What could I do to get the I out of the bottom there, do you suppose? Any ideas? Okay, the multiply by I, I'm seeing, and I'm seeing multiply by 2i. Those are both good answers, but what do you mean multiply by I or multiply by 2i? Multiply what by I or by 2i? Top and bottom. Okay, good. Top and bottom, right? I have to multiply the top and the bottom by the same thing, so I end up multiplying by 1, right? The fraction 1. I could multiply by 2i, but I want to make this as easy as possible. So why not just multiply by I? So I get smaller numbers, right? What's that going to give me on top? So on top, I'm going to get 10, and I could have reduced that earlier. I could have made the 10 over 2 of 5 over 1 too, couldn't I? Right? So on the top, I'm going to get a 10i. On the bottom, I'm going to get 2 times I squared, which is negative 1, right? So that's just a negative 2. So I end up with negative 5i. Everybody see that? Okay, that's no big deal. If I have a single I on the bottom, it's really simple to divide these out. All I've got to do is multiply the top and the bottom by I, right? So let's do one more. What if we look at like number 15 here? Okay, what about number 15? Well, first of all, I didn't simplify, I didn't reduce the fraction in this first one, but I can here, right? So one thing I could do is I could split this up into 20, and I could probably do this in a single step. 28 over 4i minus 8i over 4i, right? And look what happens when I do that. The i's cancel there, and 8 over 4 reduces to 2, right? What about here? The 28 over 4 reduces to 7 over 1. And so that looks like 7 over I minus 2. Everybody agree? Okay, so this one's already done. This term is already done, but this guy here I need to multiply by I over I, right? And what's that give me? I end up with 7I over I squared is negative 1 minus 2. Well, I want to write this as a complex number in standard form, so I need to put the real part first. There's my negative 2. And then 7 divided by negative 1 is just negative 7I. Everybody see that? Okay. Did I have to do it that way? No. I mean, I didn't have to simplify first, reduce the fractions. Let's look at one where we don't reduce the fractions first. What if I took this one right here and I just multiplied this top and bottom through by I? What's that going to give me? Well, if I distribute on top, I'm going to get negative 8. Boy, this pen. I got a new pen coming, just so you know. It's on order. Minus 8I minus 2I squared is plus 2, right? And on the bottom, I get 6I squared is negative 6. Now I could split it, right? So let's put this fraction first. Let's put the real fraction first. Negative 2/6 plus negative over negative is positive 8/6I, and then I could reduce those. Negative 1/3 plus 4/3 I. Either way, I would do it the way we did in 15 personally, but either way works, okay? Okay, so now that's what we do if we've got a complex number. We're simplifying a complex is.
No, my phone is cutting out again.
Oh, is it? Okay.
So it gets like.
Oh, okay. Gosh, I wonder why it's doing that. Let me see if I can change a channel on it or something here. Huh. Is that better? Okay, we'll try it one more time here. If it gets bad, let me know. So if the denominator is a pure imaginary number, so it's only got an I term, it doesn't have a real part, then that's really simple. You just multiply the top and the bottom by I. Okay, but what if the denominator has both a real part and an imaginary part? Okay, so it's neither a pure real nor a pure imaginary number. It's a binomial, right? It's got both parts. Then what do? Well, then we're going to multiply the top and the bottom by the complex conjugate of the denominator. Okay, how come? It's a good strategy, isn't it? Because remember what happened when we multiplied two complex conjugates together? We always got a real result, right? The i's disappeared, okay? So that's our strategy. We're going to multiply the top and the bottom by the complex conjugate. So in this case, to simplify this quotient right here of complex numbers, I would multiply the top and the bottom by 4 plus 6i. So let's do this and see what happens. Okay, and we're going to multiply this. We're going to multiply this through by the complex conjugate of the denominator, top and bottom. Now, we already know what we're going to get on the bottom. What's it going to be?
A squared plus B squared.
Yeah, good. 16 plus 36. Good. Okay, what about the top? Well, on the top, we've got to FOIL this out. So we'll distribute the 6 and get 24 plus 36i. We'll distribute the 4i and get plus 16i plus 24i squared Well, what's that going to be? What's 24i squared? Negative 24, right? The I squared becomes negative. Good. So all this just becomes minus 24. Okay. And then we can combine like terms on the top. And so what do we get then? We get 24 minus 24 is 0. 36i plus 16i is 42i divided by 16 plus 36 is what, 52? So we end up here with the result, what's that going to reduce to? 21 over 26. So 21/26i is our answer. Okay, makes sense? Okay, let's try another. So what about this guy? Here we're just going to, we're going to multiply top and bottom this time by the conjugate, complex conjugate of the denominator, right? Okay, so that's going to be 5 minus 6i. And then what's that going to give us? So on the bottom, we're going to get 5 squared plus 6 squared. On the top, if we FOIL, 15 minus 18i plus 25i minus 30i squared, which is the same as plus 30, right? Okay, and then we can just add like terms up here. So on the top, we're going to get, let's see, 15 plus 30 is 45. Negative 18i plus 25i is plus 7i over my common denominator of 25 plus 36 is, what is that, 61? Okay. And then now I will just, I want my answer to be in the form a plus bi. So I've just got to split this thing up then into a real part and an imaginary part. So I just split my common denominator. So I end up with 45/61 plus 7/61 I. And I would reduce either of those fractions if I could, but I can't, right? Okay, that makes sense? Got the idea? Okay. All right, so now we get into something kind of fun. So why do we deal with all these complex numbers? You might be asking yourself. I mean, is this just some mathematical weirdness? You know, I alluded to this the other day, but complex numbers with imaginary parts are really important to us in math and science. In physics, you deal with them all the time. They're just different, but they're not any less valuable than real numbers. What are real numbers really for? Well, they're kind of for counting, right? That's what they do, is they count. But there's some other things that complex numbers do a lot better than real numbers, in a sense, right? So here's an example that I cooked up for you. This is a pretty good one. So I'm going to give you a little background on this too. Some of you might find this interesting. If you're kind of leaning towards engineering or science, this might be something that'll tickle your fancy a little bit here. So complex what is impedance? When you're talking about circuits, like an AC circuit. So this is going to be a circuit like that would be driven by an alternating current, like your line voltage in your wall sockets, right? So impedance, what does it mean to impede something? If you're impeding something, you're obstructing it, right? So impedance refers to the obstruction of the flow of electricity, is one way to think about it, through the circuit. Okay, there's a complex impedance. Z is usually the variable that we apply to complex numbers for some reason. I think it is partly why, because that way we can let X be the real part and Y be the imaginary part. Well, if we have a complex impedance like this, the real part of the impedance is what we call the resistive impedance. So this is true resistance. This is energy that is lost in the circuit to heat. This would be like, for example, when you turn on a light bulb, like think about an old-fashioned incandescent light bulb. They get pretty hot, don't they? Right? Because in the process of generating that light, which is the useful part of the light bulb, most of the power is actually lost as heat. Very little of the energy is actually turned into useful light. Most of it is lost as heat. And that's why LEDs are far superior than incandescent light bulbs. You know, the old-fashioned incandescent light bulbs, really all they are, an incandescent light bulb is just a tungsten filament. It's a really thin strand of tungsten wire. When you pass a current through it, the tungsten is a resistor, and it literally just heats up to be white hot. And that's what emits the light, okay? Now, in an LED, a light-emitting diode, that's a much, much more efficient process where the energy and the electrical energy in the circuit is much more efficiently turned into light. And you'll notice, like if you have, I'm sure most of you probably have LED bulbs in your house now. When you handle an LED bulb, they never really get very hot, right? There's not very much heat liberated. Even for a really bright light, there's very little heat liberated, okay? So the real part of the impedance is resistive impedance. That's energy that is lost through resistance, like the burners on your stove or the filament in a light bulb, okay? Now, why the imaginary part of the impedance, this is called the reactive impedance. And there is no energy loss here. This is literally just like energy that is absorbed and returned to the circuit in slightly different ways, okay? And so I'll talk a little more. I mean, it's going to be hard for me to say too much about this because you guys haven't really had any classes in electronics, but I can give you a little flavor of this. So if we're going to make some analog circuits are non-digital circuits. So they're the circuits that would be in your toaster, or in, circuits that would be in your receiver, in your stereo system, right? Or in your speakers, okay? These aren't digital, these aren't digital circuits that are printed on circuit boards where it's a logical, it's all encoding signals in binary and decoding them in the circuit with electronic. You're sending electronic signals through the circuit that carry the digital information. That's more complicated. This is really simple. This is literally just electricity flowing through a circuit and doing something for you. Either it's going to make sound in a speaker, or it's going to make your toast hot in a toaster, something like that, right? So there are only 3 different components in analog circuits. There are resistors, which are like burners on a stove. There are inductors, and inductors are just helical coils of wire. So think like a tube. It literally looks, see what I'm pointing at right there? It just looks like that. It's just a wire that's bent into a helical shape where it creates this hollow core, and the wire just is like, it's like a circular pattern, like a slinky. Think about a slinky. You guys have all seen slinkies, right? That looks like an inductor. And then a capacitor is just 2 conducting plates that are held very close together but not touching. So there's a gap between the plates, okay? Those are the only 3 kinds of components in an electrical circuit. Inductors tend to slosh any current that flows through the inductor. The magnetic field that's generated in the conductor induces an electrical field, which tends to push the current backwards. It kind of sloshes back against the flow of the current. And so you're storing some energy that way. It kind of washes around back and forth. In a capacitor, it's a little bit different. The current is stored on the plates until the electric field becomes so high that the current leaks across through the electric field. Okay. And so both of these introduce what's called a phase change, which means that the original signal that's coming in is either slowed down or speeded up, okay, relative to where the original signal that was coming into the circuit, what it looked like, okay? And you can take advantage of these things. Like, for example, here's a speaker I'm building right now. This is just an electronic network where when the signal comes in from my amplifier, it's going to be split into these different pathways. And by using these combinations of resistors and inductors and capacitors, I'm able to build high-pass filters and low-pass filters where I can take the sound signal and either filter out all the low-frequency signal so I can send that part onto the tweeters, which are the high-frequency speakers, or I can do the opposite. I can filter out the high-frequency signals and send the low-frequency signals to the woofers, the really large drivers that give you the bass. And then in the mid-range, you kind of do a combination of both of those things, right? But this is just an example of using those three components. There's an inductor, those are resistors, those are capacitors right there. Those big things are rolled up capacitors where the plates are almost touching, but they're rolled up into a tube, essentially, okay? We're out of time, but I'll tell you some more about this, and we're actually going to calculate some complex impedances, which is kind of cool. We can actually use these complex numbers to do some real electronics work here. We'll do that next time. All right. Have a great day. I'm here after school if you need me. Otherwise, I will see you.